Okay, let's briefly review part 1 first. In part 1, we used the generalized Weierstrass representation formula to describe a minimal immersion in R4 with embedded planines. Here, we denote that an end is an embedded planine if the following three conditions are satisfied. First, it is asymptotic to a plane. And it is a graph over that plane outside some compact sets, and also it has no logarithmic growth. Then we say that an end is an embedded planar end. These conditions are expressed in terms of differentials as follows. The order of the pole is 2 and it has no residue. And by constructing a basis for the space of melomorphic 1 forms with n-most double poles at given points, we finally obtain the following expression. So the existence of such minimal emergence is equivalent to the existence of omega i's, and here the coefficients, such that they satisfy these conditions. We will use this equivalent formulation to prove the main results. And we say that a minimal surface has ends like the Lagrangian catenoid if it has two embedded planines and the Gauss image of the ends are on the same ruling. Okay, now we state our first main result. Theorem 1 is that there is no genus 1 complete minimal immersion in R4 with two embedded planines. As a remark, consider VD for a given divisor D. Here, for example, consider D as follows. Then it is well known that VD is a real vector space of dimension 2 times of the degree of D. So P1 plus P2 is a real vector space of dimension 4. Now, if we consider the problem of two embedded planines in Rn, then we have n melomorphic 1 forms where it is contained in this V P1 plus P2. As it has real dimension 4, so the resulting minimal surface should be contained in some four-dimensional affines of spaces. So it is in R4, in Rn. This implies that the same result also holds in arbitrary Rn. And also, since the condition for the position of the end is not given here, all possible end positions are included, such as like this, or this, or this. All cases are included. Okay. In order to prove theorem 1, we need one more thing. It was originally proved in R3, but the same proof without any modification still works in R4. So we introduce the Consonant Theorem in R4. Here, mu m is defined as follows. For a point P, mu P denotes the number of sheets passing through P. So mu P is the number of sheets passing through and mu m is maximum of them. So for example, if we have a shape like this, here point A and here is the point B, then by definition mu A is 1 and mu B is 2 because here 2 sheets. So we see that mu of this shape is equal to 2. So it is a maximum multiplicity of a surface, and the theorem says that for an immersed minimal surface with embedded plana ends, it is less than or equal to the number of ends. The original proof uses the conformal invariance of the squared L2 norm of the traceless second fundamental form and also the conformal invariance of the mean-quarter spheres. And also it uses the Liao inequality for the Wilmer function. And now it is easy to see that all these objects still work in R4. So for more details, we may refer Kostner's original paper. Now we prove theorem 1. Consider a fundamental domain, and without loss of generality, we may assume that P1 is the origin. Holomorphic one form here can be chosen to be dz and let P be a corresponding Weierstrass P function. And let us denote E1, E2, and E3 as follows. Then we have the following relation. On the other hand, as P has double poles at the origin, we may choose eta 1 as follows. And here are two cases for P2. The first case is that and the second case is the following. In each case, we may choose eta 2 in the following form. So in the first case, eta 2 can be given by like this. Over dz. And in the second case, eta 2 can be given by this. Okay, let's start with the first case. By the expression we found in part 1, we may write differentials by our choice. So dz plus a1 eta 2 and phi 2 is d1 eta 2, and we have these conditions. Now, by a simple computation, this identity is equivalent to the following. So it is and P prime is equal to here plus 2 times plus this. So it is equivalent to this wrong equation, where this wrong equation holds for z. And by squaring both sides and applying the above relation, where we have here p prime and we have relation for p prime square here. So by squaring both sides in here and applying that relation, it follows that this square p minus e1, p minus e2, p minus e3 is equal to this. Plus 2 times this square for over z. So if we think of this as a polynomial equation in P, so if we think of this as a polynomial equation in P, then it should be an identity, because the Weierstrass P function takes infinitely many values. So now, comparing the coefficients of both sides, we finally arrive at the following result. So in the end, we can conclude that this and this, since phi 1 and I phi 1, which is equal to plus minus phi 2, have no real periods, we may conclude that phi 1 has no period. And similarly, all differentials have no period. Now we obtained well-defined meromorphic functions by taking the integration of these meromorphic 1 forms. They are well defined because we show that they have no period, and it has simple, only one simple pole. They have only one simple pole. Um, so so sorry, I will change something. So if we see this phi 3 and phi 4 here, it has only a pole at P2, and by taking the integration of these meromorphic one forms, we have um, meromorphic functions with only a simple pole. So, and at least one of them is non-trivial, so it is a contradiction. Because if there is a non-trivial meromorphic function with only a simple pole, then this implies that such Riemann surface is biholomorphic to P1, which is a sphere, so it is a contradiction. Now we move on to the second case. So and in this case, eta 2 was given by this. Now consider a transformation I given by Iz is equal to minus C, and it gives rise to an automorphism of sigma. Then we compute pullbacks by I. So pullback of dz is minus dz, and pullbacks of eta 1 and eta 2 are minus eta 1 and minus eta 2 respectively, because we know that the Weierstrass p function is an even function. Hence, we finally obtain that pullbacks of meromorphic one forms phi I is equal to minus phi I for all I. Now, suppose that the immersion is given by this. Xc is real part of C from C0 for some C0. Then we compute the point xiz. So we have that xiz is, by definition, it is from z0 to iz of phi 1, phi 2, phi 3, and phi 4. And we separate this into like this, C0 to IC0, and from IC0 to IC. Denote here the first part as x0, which only depends on z0, and then we may write this like this to pullbacks of I, and we know that this is equal to minus phi 1, phi 2, phi 3, and phi 4. So it is equal to x0 minus xc. Now I fixes the point in here, so for a point Q in minus P2, we have that xq is x0 minus xq, so therefore xq is 1 over 2 x0. And here this set has 2 points in it, so by Consonant Theorem, it should be union of planes. So it is also a contradiction, and now the theorem 1 is proved. Now we state our second theorem. The theorem 2 is that there is no hyperelliptic complete minimal immersion of finite tonal curvature in R4 with two ends like the Lagrangian catenoid. By summarizing the key points when genus is 1, we have two main points. First, we were able to reduce the possible cases by applying automorphisms of a given Riemann surface. Second, by applying algebraic method and involution, we could prove each case without solving any period problems. Although the automorphism group has become very small in genus greater than or equal to 2, we may proceed the same idea in the hyperelliptic case because they are given by the polynomial equation and there is a hyperelliptic involution. Indeed, for a hyperelliptic Riemann surface of genus G given by this equation, and a point xr, yr on it, we may choose eta for this point as follows. So it is given by this over r square x over y if yr is non-zero, and if yr is 0, then it can be given by this. And here holomorphic one forms are given by this from 1 to g. And now the similar idea gives theorem 2. As a remark, we know that genus 2 is always hyperelliptic. And also the same results hold in arbitrary Rn. And for non-hyperelliptic case, we are not able to prove all cases by algebraic method, and some period problems remained. For example, let the genus be 3. Although it has an advantage that it is a plane quality curve, smooth plane quality, algebraically one can find meromorphic one forms satisfying all the desired conditions except the period condition. So we need some new method to overcome this problem. And finally, we give some examples when the number of n's is greater than or equal to 3. So we confirm that there exists genus D, complete minimal immersion with 2D plus 1 embedded planines in R4. And here, D is non-negative integers. These surfaces are constructed on hyperelliptic curve, and they are symmetric to the origin. Also, they are holomorphic in C2. By this observation, we have the existence of three-ended torus in R4 where there is no such immersion in R3. Okay, I will finish this lecture with some open problems. I wonder if there is a general relationship between the genus and the number of embedded planines and the ambient dimension regarding the existence. So this is problem 2, and the problem 1 and problem 3 are special cases of problem 2. So this is the end of part 2. Thank you everyone for listening.